Hi, in this video, we're going to build a model of a transmission line and run some simulations to see its behavior using SerDesPy, a free Python package for SerDes simulations. I'll be explaining how to do this, but skipping over a few of the details that I went over in the first video, where I explained how to install SerDesPy and some of its basic functionality. So I suggest you check that video out first. We'll be considering the diagram shown at the top of the slide. It consists of a transmission line, which could be a coax cable, a twisted wire cable, or a circuit board trace, as well as a termination and source impedance. Each is 50 ohms. We can apply a transmitter waveform here at Vin and read the received waveform at Vout. We'll be interested in the frequency response, the time domain response, and even plotting an eye diagram at 100 gigabits per second using 4PAM signaling. Zooming in on the transmission line itself, we can use RLGC parameters to describe the transmission line. You can think of the transmission line as two parallel wires or conductors separated by an insulator or dielectric. The figure at the bottom shows an infinitesimal segment of these two conductors. And you can see R is the resistance, L is the inductance, G is the shunt conductance, and C is the shunt capacitance. And all of these parameters are specified per unit length. Also, an important transmission line parameter is Z0, which is the characteristic impedance of the transmission line. You can see how it's calculated at the bottom of the slide, or you can think of it as the input impedance to the transmission line if the transmission line is infinitely long. So Z0 does not depend on the actual length of the transmission line. Now we're going to check out the code to see how we calculate these parameters. First, these parameters can be frequency dependent. And so we're going to specify our frequencies at omega naught, which is our parameters are going to be specified at omega naught, which is 10 gigahertz. Next, we're going to specify a loss tangent. Now, there are a lot of things that go into accurately calculating a loss tangent. It kind of describes how good the dielectric is at being an insulator at high frequencies. However, if you know exactly what cable you're going to be using for your transmission line, and you have the data sheet, you can usually read the loss tangent directly off the data sheet. Also, since we're going to be using high frequencies, we need to consider the skin effect, which effectively increases the resistance at high frequencies. We also have a DC resistance of our conductors. And now we're going to build a frequency vector to specify all these parameters at a range of different frequencies. We're going to pick F max to be 10 to the power of 12. This is the maximum frequency that we're going to specify our parameters at. And it's important to choose a really large number because this means when we take the inverse Fourier transform, we're going to have a really small time step, which will give us a good time domain resolution for our eye diagrams. We're going to specify a frequency vector in hertz and also in radians per second. And now we'll set up a few constants that'll be useful. One is the speed of light, and one is the permittivity of free space, epsilon naught. A few more transmission line parameters that will be useful are epsilon r, which is the relative dielectric constant. It's the ratio of the permittivity of our dielectric to the permittivity of free space. Using this, we can calculate the propagation velocity of our transmission line. Also, we're going to be using our 50 ohm characteristic impedance transmission line. Since we have 50 ohm source and termination impedance, it's important to have a 50 ohm characteristic impedance, because if you have a mismatch in the different segments of your transmission line, it'll cause reflections, which will worsen the signal integrity. Now we're ready to calculate the inductance and capacitance at DC for our transmission line. I'll give you a quick idea of how we're calculating these. You can see that Z0 is given below, but we also know that we want a really low R value because we want a good conductor, and we want a really low G value because we want a good insulator. So this term is going to be dominated by L because R is really small, and this term is going to be dominated by C because G is really small. And so we can basically write Z naught equals square root L over C. We also have another equation for the propagation velocity. The propagation velocity V naught is equal to 1 over the square root of the DC inductance per unit length times the DC capacitance per unit length. Using these two equations, it's pretty easy to calculate the DC inductance as follows: Z naught over V naught, and capacitance, 1 over Z naught times V naught. We also have the conductance of our dielectric, and we can write the AC resistance in terms of the skin effect factor. Now we're ready to calculate the RLGC parameters. So R is a combination between a DC and AC resistance component. L, we're assuming, is not frequency dependent. It's equal to L naught for the whole frequency range. And this is a simplification, but it's a pretty good simplification if we're assuming that our dielectric is not magnetic. And then same thing with G, we're assuming it's not frequency dependent because our dielectric shouldn't be able to be polarized by a changing magnetic field. And finally, we're calculating C, which is frequency dependent, and we get larger shunt capacitance for larger frequencies because of this theta naught loss tangent term. We're also going to be using a 10 centimeter long transmission line. So now let's go back to the slideshow and see how we're representing this transmission line as a two-port network. A two-port network looks like this. It's got one port on the left side, one port on the right side. Each port has two terminals, and the current entering one terminal is equal to the current exiting the other terminal. And if the network is an LTI linear time invariant system, we can characterize it using a matrix like this, which contains the ABCD parameters, and it relates what's going on at one port in terms of voltage and current to the other port. There are other ways you can specify network parameters, such as S parameters and Z parameters, but ABCD parameters are very convenient for cascading multiple two-port networks together, because the ABCD parameters of two cascaded networks is equal to just the matrix multiplication of their individual ABCD matrices. So we're going to define ABCD matrix for the source, the transmission line, and the termination. In SerDesPy, we have a function RLGC, which converts these RLGC parameters to ABCD parameters. So I'm going to run this code. And now we have the ABCD parameters for our transmission line. We can take a look at B line, and we see that each entry is a 2x2 matrix with complex values, and we have one entry for each of the frequency steps that we created, because ABCD parameters are frequency dependent. Now, our source impedance is a pure impedance, and we've got a function for creating ABCD parameters of an impedance. Our termination is a pure admittance of 50 ohms, so we have a function for creating ABCD parameters of a pure admittance. Both of these, source and termination, have the same impedance as our characteristic impedance, because if you have a mismatch in impedance, it creates reflections, which is bad for signal integrity. Finally, we can create ABCD parameters for the entire channel, which is the series matrix multiplication of the source, the transmission line, and the termination. Finally, we can calculate the frequency response, the discrete frequency response of our entire system as 1 divided by the A parameter, which corresponds to the 0, 0 entry in the matrix. You might see the frequency response defined in this way in terms of ABCD parameters, which includes more than just 1 over A. But what we've actually done is we have lumped the source, transmission line, and termination into one ABCD parameter block by multiplying the 3 of them together. And so if you look at this as a whole, it's kind of like you have a short circuit source and an open circuit termination, because these are already baked into our ABCD parameters. And so if we go back to our equation here, and we enter ZL is equal to infinity for our open circuit termination, and ZS is equal to 0 for our short circuit source, you get H equal to A to infinity over A times infinity plus some negligible terms, which basically equals 1 over A, which is exactly what we have in the code. Okay, so now we have our discrete frequency response. And using the steps that we explained in the last video, we can calculate the frequency response by taking the inverse Fourier transform, as well as the step response and the pulse response. And we can plot our frequency response and time domain response and take a look at how they look. So I'm just going to run all this code. This is the Bode plot for our transmission line. You can see that if we're using 100 gigabits per second signaling, our Nyquist frequency is 25 gigahertz with PAM4 signaling. And so the insertion loss at Nyquist is shown with this gray line. It's about minus 12 dB. And this is what the pulse response looks like. We can see a few post-cursor ISI terms. And the step response is like an exponential settling. Again, with the same steps as shown in the last video, we can generate some pseudo-random PAM4 data. We can convert it to a transmitter baud rate sampled waveform. We can oversample the waveform so that the oversampling ratio is equal to the oversampling ratio of our impulse response, run a convolution between the transmitter waveform and the impulse response of our transmission line, and plot an eye diagram to see what the eye looks like with 100 gigabit per second signaling. So here we have the eye diagram. There's no equalization on this channel at all, so you can see lots of intersimple interference, but the eye is still just barely open. Now what we're going to do is add a shunt capacitance at either side of the transmission line, which is like modeling some packaging between the transmitter and the cable. So this capacitance network can be, again, modeled with an ABCD parameter, and it's like a pure shunt capacitance. So we're using a shunt cap function. And now we're going to rewrite our channel in terms of the source impedance, the capacitance network, the transmission line, capacitance network again, and the termination. Now we can run the same steps and plot the frequency response. Here on the Bode plot, we can see that now at the Nyquist frequency, we've got like minus 16 dB of insertion loss. So the signal is more attenuated with these capacitors. you could see that these capacitors kind of act like a low-pass filter, which causes this attenuation because we have some resistance in the transmission line, and then the shunt capacitance filters out some of the high-frequency information. And also, the capacitance effectively changes the characteristic impedance of this part of the transmission line. So now our source and termination and transmission line characteristic impedance doesn't match, and this causes a reflection. And so if we look at the impulse response, you can see we have our main cursor, some post cursors, and then a nanosecond later, we have our reflection and even another small reflection. Now we can plot the eye diagram again and see how it changes. Yeah, so now the eye is not open at all, indicating that the signal integrity is much worse with these shunt capacitance blocks. Finally, I'm going to save our waveforms because they'll be useful in the next video. But that's everything for this video. Thanks for listening.